All right, so I had to stop my last video partway through this example because I was running out of space on my recording device here, but we're good now. So what we're going to do is wrap this one up by applying L'Hopital's rule. What we had noticed before was that this limit right here led to an indeterminate form because I have something of the infinity minus infinity type. So we can apply L'Hopital's rule to that, but we have to put it in the form of either a 0 over 0 or infinity over infinity type of indeterminate form. So what I'm going to do, I kind of ran out of space here. I'm going to flip this over and finish this one out right here. So really what is happening is we want to look at the limit as t approaches, we said -1, but from the positive side. And the stuff that I had in the parentheses there, if I rearrange it a little bit, looked like 1 over t plus 1 plus the natural log of t plus 1. Okay? Now, if I were to get a common denominator here, so if I were to multiply the natural log of t plus 1 times t plus 1 over t plus 1, I could add it to this term here to get a single rational expression. So I could write the limit as t approaches -1 from the positive side. That rational expression is going to look like 1 plus t plus 1 times the natural log of t plus 1 over t plus 1. Okay? Now, let's see if we have the right type of indeterminate form. So I can see if I plug a -1 in here for t, then I'm going to end up with, or if I take the limit rather, as t approaches -1 from the positive side, down here we're going to be approaching 0. Okay, here what's going to be happening? Well, I have -1. If I plug it into this guy, I get a 0, and if I plug -1 into this guy, I get something undefined. But if I approach -1 from the positive side, I'm going to end up getting a negative infinity type of discontinuity. So now we're looking at a 0 times infinity type of indeterminate form. So I can go off to the side and see what happens to this guy if I were to evaluate that limit. So down here, I'm going to say, what is the limit as t approaches -1 from the right of just that t plus 1 times the natural log of t plus 1 term? Okay? What I'm going to do is rewrite that in this form. T approaches -1 from the positive side of, let's write that as the natural log of t plus 1 over t plus 1 to the -1 power. Okay? Now, remember, this guy is going towards negative infinity. This guy down here, inside parentheses, is going towards 0, but then if I take that to a negative power, it's going towards 1 over 0, which is going to lead to another of those infinity types of divergent limits. So I'm getting an infinity over infinity indeterminate form. Okay? So that means that I could use L'Hopital's rule on that, which would be the limit as t approaches -1, but from the positive side. This guy is going to become 1 over t plus 1. This is going to become negative t plus 1 to the -2 power, which is the same thing as limit as t approaches -1 from the positive side of negative t plus 1 squared over t plus 1. This will cancel with one of these. And as t approaches -1 here, this numerator is going to be going towards 0. So this limit becomes 0. Coming back up here, now what I'm seeing is this expression up here is going towards 1 plus 0, essentially, which is 1. My denominator is going towards -1 plus 1, which is going towards 0. So it's not an indeterminate form, actually. Or it's not an indeterminate form where I could use L'Hopital's rule. Instead, it's going towards 1 over 0, which is the type of limit that leads to either a positive or negative infinity. Doesn't matter which one, because the point is that this thing is it's divergent. So going back to my original example now, flip that around. This does not exist. That limit does not exist. So I would say that this is a divergent improper integral. Now, there was a lot going on in that one, right? Because when we got to the stage where we were actually trying to evaluate our limits, we needed to use L'Hopital's rule, and we kind of needed to look at it. We needed to manipulate that function a lot before we could really see what was going on there, okay? But that's that example. Let's take a look at another one. Okay, this time I want to evaluate the integral from -1 to 8 of dx over the cube root of x, if it's convergent, or show that it's divergent. Okay, this has an infinite discontinuity when x is equal to 0, because then I'm dividing by 0. 0 is not one of the limits of integration, but 0 does fall between -1 and 8. So that means if I want to evaluate this, I have to split this up into two integrals. The integral from -1 to 0 of, and I'm going to rewrite this integrand as x to the -1/3 dx, like that. I also need to evaluate the integral from 0 to 8 of x to the -1/3 power dx. Both of those are going to require limits. So this guy is going to require the limit as t approaches 0 from the left of the integral from -1 to t of x to the -1/3 power dx. This is an easy one to evaluate. So this, I'm going to add a 1 to my exponent, which is 2/3, and then I'm going to multiply by the reciprocal, which is 3/2, and that 3/2 I can take outside of that limit as well. T approaches 0 from the left of x to the 2/3 power from -1 to t, okay? That is equal to 3/2 times the limit as t approaches 0 from the left of t to the 2/3 power minus -1 to the 2/3 power. Okay, here this function t to the 2/3 power is continuous at 0. So I can evaluate that limit using direct substitution. I could plug that 0 directly in. I get 0 here. -1 to the 2/3 power is +1, but 0 minus that would be -1 times 3/2, -3/2. Okay, let's follow similar steps here. This time I need a limit as t approaches 0, but from the right of this integral, 0 to t. Oh, I'm sorry, t to 8. I switched around where the t shows up. X to the -1/3 dx. Same integrand, or same antiderivative, 3/2 times the limit as t approaches 0 from the positive side, or from the right, x to the 2/3 power, from t to 8. This is the same thing as 3/2 times the limit as t approaches 0 from the right of 8 to the 2/3 power minus t to the 2/3 power. As before, we saw that this goes to 0 when we evaluate that limit. 8 to the 2/3 power is equal to 4. And if I multiply 3/2 times 4, I would get 6. Okay? So that is going to become 6. Now, if I add these two things together, 6 is the same thing as 12/2. 12 minus 3/2 is 9/2. So that means that this guy, the original integral, is equal to -3/2 plus 6, or equivalently 9/2. Okay, that one wasn't so bad. The last thing that we're going to mention in this section is something that we call the comparison theorem. So the comparison theorem is a way of determining whether a particular type of improper integral will converge or diverge by comparing it to another improper integral that's easier to evaluate or easier to work with. So the comparison theorem, if it shows you that a particular improper integral is convergent, it's not going to give you any tools to evaluate it directly. The best it can do is tell you if it either converges or diverges. So here's the way this basically works. Suppose you have two continuous functions, f and g, and suppose that f of x is always greater than or equal to g of x, and both of them are always greater than or equal to 0 for all values of x greater than some number a. Okay? We have two cases. If the integral from a to infinity of f of x dx is convergent, then so is the integral from a to infinity of g of x dx. If the integral from a to infinity of g of x dx is divergent, then so is the integral from a to infinity of f of x dx. And this graph gives us an illustration as to why that is the case. So notice in this graph here, as we go to the right of x equals a, infinitely towards the right, the function f of x appears above the g of x function everywhere. That means f of x is greater than g of x for all values of x greater than or equal to a. In addition to that, both functions are greater than or equal to 0 because they both lie above the x-axis. So they satisfy this criteria listed up here. Now, we have two cases, both of which are stated as if-then statements. So the first one, if the integral from a to infinity of f of x dx is convergent. So remember, what that represents is the area under f as x goes from a to infinity. So what we're assuming here is that the area under f, all this region here, that integral is convergent, which means that's a finite area. Notice that the graph of g gives me a region that's smaller than the region under f. So if the region under f is finite, then g could not be giving me an infinite area if it's smaller than the area given by f. So that means g also has to give me a finite area if I take its integral from a to infinity. That's the reason why this would imply that the integral from a to infinity of g of x dx is also convergent. Similarly, if we flip this around, if the integral from a to infinity of g of x dx is divergent, then so would the integral from a to infinity of f of x dx. And the reason for that is, again, g of x, this is the area right here for that this integral represents, everything from a to infinity under the graph of g. If that's divergent, that means that there's essentially an infinite amount of area in this region as we continue, indefinitely moving towards the right. But the region under f, like we've said before, is strictly larger in this example than the area under g. So it wouldn't make any sense for the area under f to be finite if a smaller area is infinite. Okay? That means that this would imply that integral is also divergent. So we're going to do one example, then wrap things up. We're going to say that we want to use the comparison theorem to show whether or not this integral, the integral from 0 to infinity of arctan of x over 2 plus e to the x dx, is convergent or divergent. Okay? Now, how are we going to do this? Well, this is not a function that I can figure out a good technique to integrate directly. So I don't think that it would make much sense to try and evaluate this like we have the previous examples. Instead, what I want to do is take that arctangent function over 2 plus e to the x, and I want to see if I can find a simpler function to compare it to. Okay? So one thing that I know is that the arctangent function just by itself is only takes on values between negative pi over 2 and positive pi over 2, which means for all values of x greater than 0, the arctangent function is always going to be less than pi over 2. Okay? Not doing anything with my denominator quite yet. So notice the denominator has not changed, but this numerator is larger than this numerator. So this entire expression has to be larger than this entire expression. Beyond that, this guy right here is always greater than or equal to 0. And the reason I know that is because the arctangent function, if you remember what the arctangent function looks like, it looks like this, okay? Where you have a horizontal asymptote here and another one here at pi over 2 and negative pi over 2. Since we're only integrating from 0 to infinity, we're only looking at this part of that graph, and the arctangent function is non-negative everywhere over that interval. So that means that this numerator is never negative. The exponential function is also always positive. Adding a positive number to that won't change that. So this is necessarily a non-negative number over a positive number, which means it has to be greater than or equal to 0. Remember, that was one of the conditions that were necessary for these functions here. Okay, so this appears to be an easier function to integrate than what I had before, because I've replaced a difficult function, arctangent of x, with a constant. But I can actually make it even a little bit easier to integrate. This is also less than pi over 2 over e to the x. Notice I've removed this plus 2 here. And the reason I know that this is true is because here, if I'm adding a positive 2 to my e to the x, then I have a larger positive denominator than I do over here. Or said differently, e to the x is a smaller positive number than 2 plus e to the x is. And we know that the smaller you make your denominator, if it's positive, the larger the overall expression is. So this has to be greater than this. Now, I'm going to replace this integrand with this. So this function right here is kind of like the g of x function. Okay, I can think of this kind of like my g of x. This I can think of as kind of like my f of x in this theorem right here, because notice f of x is the one that's larger than g of x. Let me integrate this from 0 to infinity because that's easier to deal with. And if it gives me kind of what I'm hoping it'll give me, I can use my comparison theorem to answer this question. So the integral from 0 to infinity of pi over 2 e to the x dx, pi over 2 is a constant. You can pull that out. This is the same thing as the integral from 0 to infinity of pi over 2 is out here of e to the negative x dx. Okay? That's the same thing as pi over 2 times the limit as t approaches infinity. Remember, we'd replace that infinity with a t. I'm going to go ahead and evaluate this definite integral, though. I have negative e to the negative x from 0 to t now. Okay, this is pi over 2 times the limit as t approaches infinity of negative e to the negative t minus negative e, so that's going to become a plus, so I'm subtracting a negative, e to the 0, which is the same thing as 1. Okay, as t goes to infinity, negative t is going to negative infinity, and e to that is going to 0. So this goes to pi over 2 times 0 plus 1, or just pi over 2. Okay? Now, because that is finite, this integral converges. But that means that the integral of the larger function converges, or that's like case A here, the integral from 0 to infinity of f of x dx is convergent. Therefore, the integral over the same interval but of the smaller function has to also be convergent. So I can say something like this. By the comparison theorem, the integral from 0 to infinity of arctan of x over 2 plus e to the x dx is convergent. Okay? And that's it. So that covers everything in chapter 7.